non-spontaneous. If I were to pair it with a reaction that I know is spontaneous, such as D plus E gives me F, is if I know that this is a process that if I know that this is a process that the delta G is, let's say, -7, in order to make A plus B happen, even though it's not spontaneous, I can add those reactions together. And the result is A plus B plus D plus E leads me to C plus F. And because we're adding those reactions together, their delta G's add up. So our delta G is now -2, which is a spontaneous process. So you've made magic. You've turned a non-spontaneous process into something spontaneous by coupling it to a spontaneous one. And usually this D plus E equals F that we use to couple a non-spontaneous reaction is usually ATP decomposed into ADP and P. Just something to keep in mind. Okay, now nugget 1 tells you the basic rules. Nugget 2 tells you that if you have a reaction, you want to break it. One way to change the fate is to couple it with something exergonic. But what if we don't have D plus E equals F? What if we don't have this coupling thing? How can we still make it spontaneous? Remember that a delta G of a reaction, if it's not in standard state, so not in standard state, standard conditions, is equal to the delta G in standard conditions plus RT ln Q, where the Q is the concentration of the products over the concentration of reactants in a state not in equilibrium. And so this is a way for you to figure out the delta G in a standard in a scenario where you're not in equilibrium, not in a standard condition. And then you can do delta G in standard condition, which is usually in equilibrium, plus RT ln Q. And so one thing to note is, let's just say, let's take our example, A plus B becomes C, and that's delta G equals +5. And let's just say that's delta G standard. I'm just gonna say delta G with a 0 is standard. So the delta G standard is +5. This process overall, endergonic. How can we make it spontaneous without coupling it to another one? What we can do is, let's say I have a reaction, delta G. So let me give you an equation. Delta G equals delta G standard plus RT ln Q. We said we want delta G to be negative because we want it to be spontaneous. So let's just say I want to make it -2. And I know my delta G standard for this reaction right here is +5 plus RT ln Q. If I do algebra, that will tell me that -7 equals RT ln Q. Without going too much into specifics of that, what that tells me is that ln Q, because I know RT is R and T are both positive, ln Q must be less than 0. And if ln Q is less than 0, that tells me Q must be less than 1. And then if Q is less than 1, that tells me that products is less than the substrate. So even though destiny in the case of delta G naught tells us that A plus B equals becoming C is an endergonic process, if we have very little C compared to large amounts of A plus B, we can actually make the reaction happen because of this RTLNQ. So this is how concentration can affect the delta G of a reaction, regardless of this delta G0. If you really want to make a reaction happen, just reduce all the products and add a super amount of the reactants and you'll make it happen. So for example, let's just say if you have a reaction that you want to happen, such as ADP plus P becoming ATP. This reaction is highly endergonic. If I want this reaction to happen, I can have a Q such that ATP concentration is way less than ADP and P. And if that is the case, then, oops, let me move that back. If I have that scenario, then RT, ln Q of that reaction will be very negative. And so as a result, we might end up making the delta G net overall negative as well. So let's look at examples on the next slide. Nugget 1, so remember nugget 1, reactions occur if delta G is negative. Well, CO2 won't just turn into sugar because it's an endergonic process. And so as a result, you need things like sunlight. So that's how plants did. If plants don't have an energy source or some kind of input, it will not happen. It's not spontaneous. Nugget 2, if you are storing energy from sugar to fat, so that's a endergonic process, you need to couple it with something spontaneous. And so what you'll learn later in the future, if you do this process of sugar to fat, which is endergonic, we actually couple it with two things. So sugar to fat is a very positive delta G, whereas ATP to ADP and P is a negative delta G. And then also NADPH to NADP positive, which we'll go over soon, is also a negative delta G. And this overall net process, if you combine and couple them together, will make the production of fat from sugar actually net delta G negative. So something to keep in mind. And then nugget 3, when ATP gets, so one thing is we always say ATP is the currency of the cell. And that's because we say that the delta G of ATP hydrolysis is negative 7.5 kcal per mole. So if I take my delta G equals delta G standard plus RT ln Q, what we're saying is that in the concentrations in the cell, where Q is Q cell, I'm just going to say this is equal to negative 7.5 kcal per mole. So this is what our current background is. Now, it's negative, and that means it releases energy, which is good because we want ATP to power things that can't be powered by themselves. But we want to think of a condition when ATP, when this delta G becomes positive. So in what scenario would this delta G, which is negative 7.5, become positive instead of negative? And the only way that would happen is if this RT, L, and Q becomes super positive. Q becomes very positive. I apologize that my formatting. The only way for that to happen is if the L and Q becomes very positive. And so what that means is that Q must be way, way larger than 1. And the only way for that to happen must mean that the product must be greater than the substrate. Or alternatively, if you want to think about ATP and ADP, what that means is that ADP concentrations must go higher than ATP. So if the cell ever gets to a point where it consumes so much ATP that this ADP becomes overwhelmingly higher than the ATP, this RT, L, and Q will become so positive that the delta G of ATP hydrolysis will become positive, which is bad. Delta G, ATP hydrolysis is our fuel in the cell. It's our currency, so it's bad. So that means this poses a problem in that we now need to keep ATP concentration to ADP concentration high. We need to make sure that there's a lot more ATP than there is ATP, or there are a lot more ATP than there is ADP. That way, this delta G never becomes positive. And so to do that, the cell actually uses up the ADP it previously produced from the hydrolysis and combines 2 of them to produce ATP and AMP. Basically, one ADP gives up the phosphate to the other, forming ATP and AMP. And that way, you replenish the ATP and you reduce the ADP. So as a result, this ratio remains high. If this ratio remains high, for the sake of our reaction, this will keep delta G negative. And if delta G remains negative, it remains a good source of energy for the cell. So that's why Rainer Heiden loves to ask you, what is the energy state of the cell? If you say I have 1 million ATP molecules, that doesn't necessarily mean anything. Doesn't mean anything without context. If you put it with the context that you have 1 million ATP molecules and 2 million ADP molecules, that should tell you then that Q, which is ADP, P, I'm assuming that the P molecules are about the same as the ATP. This number, Q, is going to be greater than 0 or 1, for sure, which would tell me that the ln of Q is going to be very positive, which would tell me that delta G of ATP hydrolysis is not favorable. So, if you learn anything today, remember, you can make something spontaneous by coupling it to something, but you can also make something spontaneous or non-spontaneous if the concentrations are in a point that you can change delta G. And that's because of this equation from last slide. Oops. This RT, L, and Q is dependent on the concentration. And this can affect the delta G of a reaction at any given moment. And so for the sake of us, if you want to think of energy of a cell, the energy balance of the cell isn't in the number of ATP molecules, it's in the ATP to ADP ratio. So if you want to compare two cells about how much energy they have, don't compare raw numbers of ATP, compare ratio, because it's the ratio that determines the delta G. And it's the delta G that tells you how good of it as a currency for energy. Okay, if you have any questions, feel free to email me or post in Piazza or go to office hours as usual. And next time we'll be going over glycolysis And so we will be going over a lot of pathways. So just look forward to that. And I'll see you guys next week. I will try to do a Zoom next week. I didn't do it this week because there are people taking the exam still. So, but yeah, feel free to do message anything. Other than that, I'll see you guys next time.